Okay, so you can calculate the total displacement of this person here by just calculating the areas under each and every section of that graph and then adding them up. So you can see that in that section the area is 3, and in that other section the area would be 0 when the person was resting, and then finally there in this case our area becomes a -4. So you have to add all these numbers together and you get a total displacement of 14 meters. So that would be your 15 plus 3, that's 18, minus a 4 there, of course, plus a 0 there, minus a 4, 18 minus a 4, that would be your 14. So it's important to know that the area under a velocity time graph will give you the total displacement. Okay, let's look at a different one where the velocity is not constant but it changes over time. Okay, so again gradient of a velocity time graph will give you acceleration, and our phrase for gradient is rise over run. So your rise over run here will give you your acceleration. Okay, so look at this graph here. We also looked at it in our lessons. So we said here, if you check just commenting on the movement of this particle, you realize that it starts off with a negative velocity here. So this is not possible, remember, with the speed time graph. This is only possible with the velocity time graph because velocity is a vector and it can have a negative value. So it's starting at -2, it goes up to 0 here and then passes that into the positive values of velocity. So this denotes a change in direction. It's a change in direction, and you can see in the first part here that the acceleration was constant, and you can tell here that the acceleration is 0, and you can tell here that the acceleration is negative. That would be a deceleration, and again we have a positive acceleration there. So we did this question where we're calculating the acceleration on each section, for each section of that graph, and we saw that for the first section your rise over run would be your 6, your plus 6 over 3, and that would give you a plus 2. In the second section of that graph it was a 0, and we saw that in that other section that would be your run. Your rise is going down, in this case -4, and if you divide that you get a -1. Okay, so your rise over run is going to be your -4 divided by your +4, and in the last section your run is 2, your rise is +1, and run over rise over run, that would be 1 over 2, and that gives you 0.5 meters per square second. And you can see from this graph that this acceleration here is larger than this acceleration here, and you can tell that this graph looks steep than this one, as we saw in the previous slides. So that's important, and when your gradient is 0 there, when you have a horizontal line, your acceleration is 0. So it means, does this mean that the object is stationary or not moving? Not. So when your acceleration is 0 there, it doesn't mean the object is not moving, because we see here that this object has a velocity of 4 meters per second, but an acceleration of 0. So it's actually moving at constant velocity. So that is what it means. So a 0 acceleration does not necessarily mean the object is not moving. You need to check if it is moving at a constant velocity. So in this case, you see it's moving at a constant velocity. Okay, so this is a negative acceleration or a deceleration. So an acceleration of -1 or a deceleration of 1 meter per square second. Okay, so those are some of the things to look out for on these graphs. We also looked at this example where you were supposed to find the total displacement of this object, and you had to just divide the area under the graph into different shapes. So that's a triangle there, and if you use your half base times height, you would realize that you get an area of 3, so that gives you a displacement of 3 meters. That would be a rectangle with an area of 12, and that's these two shapes can be divided with we have a rectangle here and a triangle, and the rectangle is 6 meters, and this gives us 3 meters. So our total displacement, we just add all of that and get a 24. Okay, so after the velocity, the speed time graph, velocity time graph, we went on to talk about the kinematics equations. Those 4 equations showing to my right there, you must know them. They are used to describe motion of objects without reference to the forces that cause the motion. We say that kinematics is special in the sense that when we are doing our calculations, our kinematics calculations, we do not refer to the newtons nor the mass of the object. The force that's causing motion and the mass of the object that's in motion, we don't even care about those two when we are doing our kinematics with these equations. So they're special in that case. They work for any object of any mass, and the forces that cause the motion are not even taken into account. We simply need those 5 variables: your displacement, your initial velocity, your final velocity, your acceleration, and time. And take note here that all these other these first 4 are vectors except for time. Time is the only scalar in these calculations. So let's look at how these formulas are derived. So we saw that you can derive these formulas using geometry. So we're going to prove the formulas using geometry. So let's look at a velocity time graph, and imagine here an object moving at constant acceleration there. We say the gradient is for the acceleration. So you should recall here that the gradient of this velocity time graph will give you acceleration. So that's an object moving at constant acceleration. So I would like to put labels on this graph. So to begin with here, let's imagine our initial velocity represented by u. So that's the value for initial velocity, indicating the initial velocity, that's the value. And our final velocity is this value here, that's final velocity. So with that in mind, let's also now try to divide our final velocity into 2 sections. So that's the first section, and the second section would be equal to our u. So this should make sense that our final velocity is given by those 2 values, your initial velocity plus another value that we do not know. So how do we find the other value? We can go to acceleration and calculate that. So we are saying our final velocity is u plus that value in question. So how do you find that value? You can go to acceleration and say acceleration, or your gradient is equal to rise over run, and your rise is that this section of the line here is that we're looking for. This is our rise, and our run is t. Okay, and we can make rise the subject of the formula there and find that the section that we're looking for is given by at. Okay, from our formula for acceleration. Now when we put this together, we have our final velocity is equal to this value that was here, our u plus our at, and that gives our first formula. So we're just looking at the geometry there. So let's continue in the next video and look at how we can derive the rest of the equations.